Hey Ramblers, this video covers chapter 9.5 in our textbook and is titled The Distance Formula. But the material in it really extends beyond just the distance formula to cover coordinate proofs altogether. Now I know I just told you we're done with proofs for the year, and we're pretty much done with two-column proofs, but coordinate proofs are being taught here because they're very important in later math classes. A coordinate proof takes a geometric figure, puts it on the coordinate plane, assigns coordinates to its vertices that reflect the properties and characteristics of the figure, and then uses the slope formula, the midpoint formula, and the distance formula, which we'll derive today, to prove certain properties or certain qualities about the figure. Sounds pretty complicated, but it's really not. The proof itself is the easy part. What we're going to focus a little bit on in this video is the derivation of the distance formula, but also how to choose coordinates that reflect the characteristics of the figure that you're working with. Okay, please pay attention, take good notes, and I hope this video helps. Suppose we're given 2 points on the coordinate plane, anywhere on the coordinate plane, and we wanted to find the distance between those points. How exactly would we go about it? Well, this was exactly the question René Descartes had. And so he came up with this method. Descartes was familiar with the Pythagorean theorem, so he imagined that his 2 points had very general coordinates like x1, y1 and x2, y2. And then he imagined drawing a segment parallel to the x-axis and meeting another segment drawn parallel to the y-axis. Since these 2 segments are parallel to the axes, just like the axes, these segments would be perpendicular, so they would form a right angle. That means we could apply the Pythagorean theorem and solve for the distance between A and B as the hypotenuse. So Descartes figured that the horizontal distance would be the difference between the x-coordinate of B and the x-coordinate of A. That difference is found by subtracting x1 from x2. He knew that the vertical distance would be the change in the y-coordinates, so y2 minus y1. That would make the distance between A and B, or the hypotenuse, be the square root of one leg squared plus the other leg squared. And that's the distance formula. Make sure you get that in your notes, and we'll move on now to coordinate proofs. Coordinate proofs really have 2 parts. The first is the setup of the proof, and the second is the proof itself. Strangely enough, the setup is the hard part. The tools we're going to use, I put together in what I call the coordinate proof toolbox. The midpoint formula, which you've learned in the first semester, is going to be useful whenever we're trying to prove bisection. The slope formula is useful whenever we prove that things are parallel, or when things are perpendicular. Parallel lines have the same slope, and of course perpendicular lines have opposite reciprocal slopes. Finally, the distance formula is used to prove that points are equidistant, or to show that 2 lengths are congruent. Okay, now that you have your toolbox, let's talk about some common figures that you need to situate on the coordinate plane so that you do 2 things. One is to label the coordinates so that you can use them in your proof, and the second is that you place them so that the coordinates reflect the characteristics and properties of the figure. For instance, let's draw a square. Now we all know that the sides of a square are perpendicular and congruent in length. So the best place to situate it would be to put one vertex at 0, 0. That vertex is at 0, 0 because whenever we use 0, 0 in our calculations, it will drop out. Then the next thing to be sure is that when we establish the coordinates, we never use numbers. Well, I mean, we might use a coefficient, but we're never going to use the actual number 4 here or the actual number 4 down here. Instead, what we'll use are variable coordinates. So the coordinate of B is going to be 0, 2a. The coordinate of C, since we know that each side is 2a, we know that C will be 2a, 2a. And the coordinate of D, again, since the sides are 2a units long, the coordinate of D will be 2a, 0. Now the reason I chose 2a rather than just a is because when you start using a coordinate proof, you may end up proving that things are midpoints, in which case you can avoid fractional coordinates by doubling the coefficient. Let's give you an example. Suppose I wanted to find the midpoint of, or I wanted to find where the diagonals bisect each other. I would draw the diagonals, but I'd have to calculate their intersection. And to do that, I'd use the midpoint formula from my toolbox. I would take the x-coordinate of point C, add it to the x-coordinate of point A, divide by 2, then take the y-coordinate of point C and add it to the y-coordinate of point A and divide by 2. That will give me AA. Notice I've avoided having a fractional coefficient of A, simply because I doubled the A as the coefficients of my vertices. All right, so that's the trick that I think you'll want to adopt and use in other proofs. Let's take a quick look then at some of the other types of figures that you're going to be working with. The next thing we should look at is an isosceles triangle. An isosceles triangle will once again label the vertices A, B, and C, but then the coordinates will take advantage of the properties of 0, 0 with multiplication and addition, and always try to put one vertex at 0, 0. But then the length of the base, you'll once again want to give a coefficient of 2. So this is 2a, 0. The reason that's 2a is because the vertex of an isosceles triangle is always directly over the midpoint of the base. You'll recall that when we draw a altitude to the base of an isosceles triangle, it's also a median. So we know that the median is going to be at the midpoint of the base. So if I make the base 2a units long, then the vertex will be at a units. It really doesn't matter what you call the y variable, because no matter what, that is going to stay b. Even if I put the point way up here, I could still refer to that point as AB, because while it matters that A is halfway between 0, 0 and 2A, the y coordinate can be anything. This triangle can be as large as it wants. There's really no property inherent in the height of an isosceles triangle. Okay, let's take a look at a right triangle. In a right triangle, we'll want to put the right angle at the vertex, and you'll put the coordinates or the legs along the axes. If you think there's going to be bisection involved in your proof, then you'll want to double the value of B and A here. Finally, let's look at a parallelogram. Now, a parallelogram gets a little bit tricky because we remember that the opposite sides of a parallelogram are congruent. So as I look at the coordinates, I'm going to start with my coordinate at 0, 0. And I know that one side will be A units long, so I'll call it A0. I could easily have called it 2A0. It wouldn't have mattered. But if that distance is A, then I'll need to use that same distance up here. So what I call this vertex at I doesn't really matter. So I'm going to say that it's BC. And where I tie in the fact that the opposite sides are congruent is here. because if my vertex was at B and I've added A units, then the coordinate of point J here will be B plus A, comma C. This is a great time to pause the video and make sure you understood that, because parallelograms are by far the hardest to understand. So if this point is B and the length of the side is A, the x-coordinate of this point here will be B plus A. The y-coordinate does not change, so that will stay C. Okay, let's take a look at how to do an example coordinate proof, and then we'll conclude the video. Let's take, for example, the following statement. Prove that the diagonals of a square are perpendicular. Well, as soon as I start thinking about perpendicularity, I should start considering my slope formula, because that's where I see whether lines, that's what allows me to prove if lines are perpendicular or parallel. So I will take the coordinates, I will take the diagonals of the square and draw them in, and I see that I have to calculate the slope of AC and BD. So let's start off with that. Now, whenever you're doing a coordinate proof, you should always label your work. So I start off labeling the slope of AC calculation. And using the coordinates that I assigned to point C and point A, I calculate that the slope is 1. Then I calculate the slope of BD. Once again, I've labeled my work, and I see that the slope of BD is -1. With all coordinate proofs, your final step should be a conclusion, pointing out what your calculations have shown you. So since 1 and -1 are opposite reciprocals, the diagonals of a square are perpendicular. And you're done. Okay, you'll have some chance in the book to do some coordinate proofs, and I've put together a worksheet which will help you situate the figures and also prove a few statements on your own. Okay, hope this helped. Be sure to go back and rewind, make sure you've covered any things that are unclear to you, and thanks for watching.